Alright, so welcome to chapter 11.1 to 11.3. Today we're going to be exploring more the idea of energy transformations and chemical energy. And then in the next lecture we'll really take a look at thermal energy. So in chapter 10 we talked about a few different kinds of energy. We talked about kinetic energy, we talked about gravitational potential energy, we talked about elastic potential energy. Oh, what else did we talk about? We talked about chemical, but I didn't really give you a formula for it. And then we talked about thermal energy. We also talked about nuclear and electric, electromagnetic and sound energy, but those are all ideas that we're going to really explore, especially mathematically, next semester. For this semester, these are going to be our big focuses here. We'll just keep the idea of, okay, well, energy can also be sound, that can be light, can be electricity, right? And we'll use these words to describe those kinds of energies for now. And then again, this generic kind of term for energy is just that big capital E, right? And so if there's a lot of kinds of energy going on in a system, we can just talk about it as E total. And you can even do like that. Alright, you got a pretty good grasp on kinetic, gravitational, and elastic energy. For chapter 11, we're really going to focus on chemical and thermal energy because honestly, this is some of what we see the most of in our worlds. And so today we're going to start out talking about transformations and how energy changes from one form to another and how to classify that. And then we'll end today's lecture with chemical energy and kind of how that relates to humans in our lives. Alright, so I'm going to ask you to take a look at this picture, and yes, it's adorable. And then kind of try and classify what kinds of energy transformations you see going on in this picture as a whole, okay, not just the bear, include the plants too. And what I'm going to do is go ahead and describe those energy transformations. Whenever I think about energy transformations, I always think about it in terms of actions or objects, and so what's going on in this picture, objects or processes. And then I then take those things and I go and transfer them as a kind of energy. Right? Okay, so in this picture, what I see is plants, right? A bear eating plants. And the plants have to get their energy from somewhere, and ultimately that comes from the sun. The sun shines on the plants and they do photosynthesis. And then that photosynthesis goes to make all parts of the plant, specifically the sugars of the plant, and we'll say that it makes the berries, right? Making. And then the bear eats the berries. And after the bear eats the berries, he just goes and runs in the woods like crazy, like for hours, because that's all bears do in their spare time. They just run, 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 run. Okay. And so then that's what I see going on in this picture. And then I'm going to come over here and think about all the kinds of energy that I know. And I'm going to classify each one of these as a kind of energy. And so the sun actually has a lot of kinds of energy. On the sun, there are nuclear reactions going on that release heat or thermal energy. And then they also release light. And the light is the portion of that plants really use in photosynthesis. So I'm going to use light here. Photosynthesis is a chemical process, right? And so there's chemical energy. There's more chemical energy and kind of chemical reactions in the process of the plants actually making the berries. And so the berries have a lot of, let's see, sugar. And in science, we tend to call that glucose, specifically, a certain kind of sugar, in those berries. And then the bear eats the glucose and has his own chemical reaction, which is cellular respiration, and it takes that glucose and it changes it to ATP, adenosine triphosphate, which is the energy molecule of animals and the human body. That ATP is then a molecule that muscles can use to have kinetic energy for our little bear to run through the woods. right? And so I want you to think about your day so far and tell me what kind of what kind of transformations have happened in your life today, and not just to you, but maybe you saw them happen. And so I'm gonna do that the same way. I'm gonna give you an event, and then we'll come over and talk about that in terms of a type of energy. So you can go ahead and do this, and maybe just list like 1, 2, 3, 4 things you did today, and pause it and try and classify those as energy. And while you're doing that, I'm going to tell you about my day, and you can play the video whenever you're ready. So today I woke up, right? That was my first step of the day, and I kind of move around my house when I wake up. And then that includes, you know, taking my dog out, making breakfast, doing whatever. And then I eat my breakfast. After I eat breakfast, I drive, usually somewhere, whether that's to work or to go have fun. Drive, right? And then when I get to work or fun or wherever, I usually move around. And most days I talk, right? In fact, every day I talk. So moving and talking is kind of where that energy winds up. Okay, so in waking up and moving around, I am taking my chemical energy, which is stored in fat because I haven't eaten all night. I take that chemical energy and I turn it into kinetic energy as I begin to move around my house. In the morning, I use a little bit of that kinetic energy to refuel, to give myself more chemical energy that can then be used for lots of things, whether that is thermal energy or kinetic energy or talking energy. I wish I made light, but I don't. Okay. And then when I drive to work, I'm going to specifically talk about my car here, right? Not what I'm doing. So my car has gasoline, requires it to move. So there's chemical energy there. It also has a battery, which is chemical energy. That gasoline goes to the engine where it gets burned and gets turned into thermal energy. And then that thermal energy is mostly used to make my car move. But there's other things too, you know, there's some electricity and things like that as well. And then when I get to work, I use all of my chemical energy, well, not all of my chemical energy, but energy from my breakfast and maybe some stored in fat cells to move around and to talk, right? Which is really just a kind of moving. That's okay. All right. So that's my day in terms of energy. And what I'm going to go on to do now is to talk about my car. And so let's just talk about a car in general. Let's say a car burns 1,000 joules of gasoline, or at least that's what I put into it. All right, but I only get a work output of 500 joules. So, well, that's kind of a ripoff. Where does the rest of my energy go? Right? And so in my engine, I am burning gasoline. And that gasoline is used to activate these little pistons in here, which get things moving and hopefully spin my tires. But what I'm telling you is that the work, right, which is force times distance, I really only get about 500 joules of work out of it. And so where does the rest of that energy go, right? And well, the truth is not all of that energy goes to make the car move. Some of it goes to the electrical system, and some of it is sound, like to make my radio go. But a lot of that is really just heat loss. And so we'll say a lot of that is, sorry about that. A lot of that is just lost to thermal energy. And whoa, Ellis, like you said, energy is never created or destroyed, and now you're talking about losing energy. What the heck? Energy is never created or destroyed. That's true, and that's still true. And so energy never, let's see, never created or destroyed. And there's a second part to that. Which is that it's only transformed. And so when I'm talking about this energy in a car being lost, well, it's not lost, it's really transformed, but it's lost for our uses, right? The heat that radiates out from a car, we call this heat loss. The heat that radiates out from a car due to the friction in the engine and the tires and just general inefficiencies in a car, the heat that's kind of radiated out to the universe is not something that I can use to accomplish the work that I'm trying to get done, right? The heat that's being lost from under the hood and on the tires and et cetera, is energy changing, and it's still a kind of energy, but it's not a type of energy that I can use. I can never recapture this heat to help me move my car a distance, right? And so it's not really used for the work that I'm trying to do. It's just transformed into a form that I can't use. And so this brings into this whole idea of efficiency, right? There is no system that transforms energy in our world that is 100% efficient, which means it converts 100% of what we put into it into usable energy. Everything that we know is inefficient to some degree. And so when I have this situation with the car, right, where I put 1,000 joules of gasoline, which is not that much gasoline, but I put 1,000 joules of gasoline into it, and I only get 500 joules out of it, well, that's kind of a bummer, but that's because my car is inefficient, just like everything else, from power plants to bicycles to your own body. And this idea of efficiency is grouped into two categories. It's what you get, or kind of like the output of a machine, divided by what you pay, what you put into it, and so we'll call this the input. And if you like these two words better, then you can, in your own formula sheet, do output over input, right? That's fine. And so I want to do a little bit of math, and I want to say, what is the efficiency of the car that I'm talking about? I put in 1,000 joules and I get out 500 joules of work. And so the efficiency of our car is going to be equal to what we get, right, or the output of it, which is about 500 joules of work, divided by the input. And when we do that, we actually have a canceling of units. And so, oh no, what is the unit of efficiency? Well, it's not a unit. It's usually expressed as a percent. When we do this math, we get this as 0.5. Efficiency likes to be expressed as a percent, and so that converts over to 50%. And if you're not sure about the math in between that, all I do is 0.5 times 100, right? Timesing it by 100 is how you will always get from a decimal to a percent. And so our car is about 50% efficient. And, oh man, dang. Well, that's okay, right? Because before you did the math, you didn't really know that, and you were willing to pay for the gas anyways. We can talk about this efficiency in terms of all systems that transform energy, right? Because all systems that transform energy have an input and an output. And I am recording this lecture on Halloween, so I've got candy on the brain. Let's imagine that you eat 856.2, that's a very specific number, but we'll say 856.2 calories of Halloween candy. How many joules is this? First off, calories is the measure of energy in the United States. It's the customary unit, like pounds or feet. Joules, right, is the SI unit of energy. And so in physics, this is what we're going to use. But you guys are used to calories, so I'm going to use that too, and we'll convert back and forth between the two. One of the most important things to know is that calories, like you see on food with a capital C, means 1,000 calories, right? 1,000 small calories. And so because it's not metric, this is our subtle abbreviation of saying kilocalories, right? And so when you're consuming something that's like 100 calories, in our terms, right, that's really 100,000 calories. And so the unit calories like this that we're going to talk about in physics is very different from the one you're looking at, right? You got to multiply by 1,000 to get there. Anyways, 1 calorie with a capital C, or 1 kilocalorie, is equal to 1,000 calories. And one of these little calories is equal to 4.19 joules. And so if I have this many, and then, ooh, there's a capital C, kilocalories, how many joules is this? And so I'm going to set up my conversion down here. I'm going to start with what I know, 856.2, and then that's going to be kilocalories, right? And I'm going to multiply that by some kind of conversion factor that I know. I've got to put kilocalories on the bottom, and I'll put regular calories up top. And so I know that 1 kilocalorie is 1,000 regular calories. These units will cancel, and I'm left with regular calories, but that's not what I want. I want joules, and so I've got one more step to do. I'll have to make sure that my units are going to cancel and put what I know about them. So 1 calorie is 4.19 joules. And take a second, pause the video, and go ahead and solve that out, right? So what is 856.2 kilocalories in joules? Alright, and we get this huge number, 3,587,478 joules. Whoa. And so when we talk about food, right, especially in kilocalories and joules, this conversion doesn't really work great. And so when we talk about joules, we should talk about kilojoules. And in this case, this would be 3,587 kilojoules, right? Which means add another 3 zeros on that. And so when we talk about food, we tend to talk about kilocalories and kilojoules because there's so much energy in food. Alright, let's talk about the efficiency of a human then. If you have a mass of 70 kilograms and an efficiency of 25%, and this is something that you might want to make a note of, right, is that when we talk about humans, they generally have an efficiency of about 25%. Now it depends on the individual human, but this is kind of like most of the time, right? And so when we talk about people in physics, we'll use that number, 25% efficiency. Okay, so if you have a mass of 70 kilograms and an efficiency of 25%, how far can you run at 4 meters per second on this? Okay. Alright, so if you have a mass of 70 kilograms and an efficiency of 25%, which is our acceptable estimate for humans, how far can you run at 4 meters a second on this? And so we are going to assume that you have just consumed all of that Halloween candy, which is, we found the equivalent to be that, right? If we go back and look at your formula for efficiency is your output divided by your input. Your input. And in humans, that is 25%, and we know that's going to be equal to 0.25, right? I know my input, I'm trying to find my output, and so when I rearrange this, the output that I'm going to be able to get out of all of that candy is going to be equal to my input energy times 0.25, right? The efficiency of me, a human. My input energy is this big long number, so we will do 3, 5, 8, 7, 4, 7, 8, joules, times 25% efficiency, and of that 3 million joules of energy, I will actually only be able to use about 896,869.5. That's a very specific number of joules. And so this is my usable energy, right, out of all of that. By the way, where does the rest of that energy go? I mean, I had 3 million joules, and now I'm down to 896,000. Well, the rest of that energy gets converted to heat in metabolism, and some of it will get stored in your body as fat as well. Right? And so this is what's immediately available for use, which is still a heck of a sugar rush. And so we know that this is the work we can get out of it, right? And we also know that work equals force times distance. So the work I can get out of this is the 896,869.5 joules. And then force times the distance. Well, I'm talking about running. And so a pretty good estimate of the force that I'm going to use to run is going to be my mass, right? 70 kilograms times gravity, because ultimately that's the mass I've got to move forward, times 9.8 meter per second squared. And then last but not least, my distance, right? And so this force I'm just getting from my mass times gravity. 70 times 9.8 is 686 newtons, right? And over what distance can I move myself if I've got this much energy to use? 0.5 joules. I will divide both sides by 686, divide by 686, and I wind up with 1,307 meters is going to be my distance. And well, does that make sense? Yeah, it does, because if I think about that in terms of kilometers, that's 1.3 kilometers, which is about a half a mile on all those calories from my stuff. Notice though, and this is kind of an interesting point for runners or anybody that exercises, that I didn't use this number at all. And that's because work is equal to force times distance. It does not take into account how fast I'm running, right? Fast is watts, and that's power. The work that gets done, it gets done no matter how fast you do it. And so technically, right, whether I run this half mile or whether I walk or crawl this half mile, I am technically, in terms of physics, doing the same amount of work. And I'm burning the same amount of calories. It's just the time that's the different part, right? There are some good references about the human body and about other things in all of this. And so we talk about this chemical energy, right, in all of these different things. And so far we've talked about gas and food. But there's energy in hydrogen, like fuel cell batteries. There's gasoline. Fat and carbohydrates are very different kinds of energy in terms of your body. Fat carries a lot more energy per gram than a carbohydrate does. We use coal in our power plants, and then wood. If you've ever had a campfire, you know that wood is capable of making energy from photosynthesis. It's those plants that have that stored energy that can be converted to thermal. And so on page 326, you find this nice little list of the types of fuels and then energy in 1 gram of fuel. And so hydrogen fuel cell batteries are so interesting because of this, right? They carry so much energy per gram of fuel as compared to gasoline, which we currently use in our cars, right? Hydrogen fuel cell batteries pack 3 times the energy of gasoline. And our cars can actually be a little more efficient and better for the environment on those fuel cell batteries. And again, in terms of things in your body, fat is a very different kind of fuel from a carbohydrate, right? So page 326, I would say this is something on your formula sheet that you just generally write down the page number of and use it as a reference. You'll also use it in your homework problems. Another really good table is the energy content of foods. And so we don't expect you to go grab a food label every time you have a physics problem that involves food. You can just reference this table. And so, you know, if you eat an apple, right, that's about 125 calories in an apple, and in kilojoules, right, and remember this big C is kilocalories, right, in kilojoules, that's about 525 kilojoules, which is 525,000 joules, right? And this list kind of goes on. It's divided into 2. So you have some foods on the left and some foods on the right. What option in this table packs the most energy? Okay, so take a look around, and oh, okay, it's over here. That's your fast food burger and fries. right, are the most energy. And what packs the least energy? Well, a carrot. Welcome to the principle behind counting calories and how food is fuel. If people go on diets and count calories, then they eat lots of these foods, not that one, empty calories. And then if people are not on diets, right, the energy content in these foods is just so much more. And when you think about, your usable energy, so you've got an efficiency of 25% as a human. Woohoo! You are a really inefficient machine. You can use about 25% of what you take in. But if what you're taking in is, 8 slices of apple pie a day, and the work you get out of that is equal to moving your mass some distance, you're going to have to go so much farther. You're going to have to do so much more work to burn the calories from these kinds of foods. There obviously is a lot more to burning calories than just force times distance, but this is the general principle behind calories and foods. All right. Also on page 327, your body actually uses energy while it's at rest, and so there's a lot of things going on in your body, right? It's not just you moving your body some force over some distance that burns calories. All of your organs burn calories as well, because while you're sitting still, there's all of these chemical processes and things going on in your body that you don't even think of, right? Your diaphragm is steadily contracting and relaxing to help you breathe. Your heart is steadily beating, and so there's still all this kinetic energy going on. Your intestines are digesting your food. Your brain is a major consumer of glucose in your body because it requires a lot of energy to learn about physics. And your liver is actually one of the biggest consumers of energy in your body because it is constantly taking your foods and inputs and detoxifying your cells, right? And then the things you put into your body. Your brain is always working, conscious and unconscious. Your heart is always working. Kidneys always working. Your muscles do kind of move. These are the voluntary muscles, and then the rest of your body, right? And so this is your energy used at rest, and it's resting power in watts, right? And now we're talking about power. And so you should be thinking that power in watts is equal to the change in energy over the change in time. It is how fast you get work done, or in the case of moving things, it's what force over what distance over what time, right? And this is something that's measured in watts. And so as a whole, your body is running on about 1,000 watts, and 1 watt is 1 joule per second, right? And so every second, your body is burning about 100 joules of energy while you're just at rest, while you're not doing anything. And then as soon as you begin to move and use kinetic energy, that number goes through the roof, right? But there's this basic kind of, your body has to have at least 100 joules a second to maintain itself, right? Because as soon as any one of these things go kaput, you die, right? And so at least 100 joules a second. And again, let's see, this is on page 327. 1 watt is 1 joule per second. And so we've got metabolic power of then, okay, well, the last table was resting. This is doing something, right? And so if I am ballroom dancing, then I am burning 250 joules per second. And your book assumes a 68 kilogram person, right? Which is pretty close to my assumption of a person, 70 kilograms. I just choose 70 because it's a nicer number to work with. Anyways, I can interpret this as 250 joules every second that I am ballroom dancing, or 480 joules every second that I am biking, or 1,150 joules every second that I am running, right? And this gets into some of the more complex issues of exercising and what's the most beneficial. And so let's imagine this question. well, let's not imagine it. Let's do it. How many joules of metabolic energy do you need to run at that for an hour, right? And so, let's see, we gotta find running. Oh, okay, here it is. Great. Running at 15 kilometers an hour. Every second I burn that many joules, right? Joules per second. And so if I'm gonna be running for an hour, we're gonna have to convert these seconds into hours, right? And so I'm gonna do that down here. And I'll start off with what I know. I burn 1,150 joules per second. And I'm okay with the joules. I just want to change the seconds into hours. So I'm going to multiply by 60 seconds in 1 minute. Those seconds cancel, and now I've got joules per minute. And that's still not what I want. And so I'm going to put minutes up top and hours on bottom, and there's 60 minutes in 1 hour. Those minutes cancel, and I multiply across the top, right? And when I do 1,150 joules times 60 times 60, I end up with 4,140,000 joules. And okay, well, this is not a number that makes sense to me as an American. I operate in calories, and so let's figure that out. If I've got that many joules, how many calories is this? And so let's see, I'm going to erase all of that work real fast. Oop. Alright, so if I've got 4,140,000 joules, how many calories is that? And I'm gonna say this is kilocalories that I'm talking about, because that makes sense to me. Right? So I know that joules has to be on the bottom, and I'm going to go from joules to regular little calories first. And I know that there's 4.19 joules in 1 calorie, and, I'm sorry, little calories is not what I want. Big calories is what I want, kilocalories, and there's 1,000 of those in 1 kilocalorie. And I'll just multiply across the multiply across the top, multiply across the bottom, and I get 4,140,000 times 1 times 1 over 4.19 times 1,000, which is 4,190. And then once I do that division, I get that I have burned 988 kilocalories, big C. And does that answer make sense to you then? Okay, well, 15 kilometers an hour is roughly 8 miles an hour, which is pretty fast for a whole hour, right? And then, okay, yes, that definitely makes sense, that's what I had to use for running at 8 miles an hour for an hour. Right? And this leads you to your homework, right? The ones on page 350 are the conceptual ones, and then 351 to 352 are the quantitative ones. Good luck, and next class we will do 11.4 through the end of 11, which goes to 11.9, right? And this is all about thermal energy. All right, happy studying.